Okay, so now we realize that electrons behave like waves, and there's this thing called the Heisenberg uncertainty principle. Says we don't really know where they are, but we're going to do our best to kind of come up with it. And so Heisenberg, another guy named Schrodinger, they came up with these solutions to some mathematical equations, really, really complex, and they determined where the electrons are likely to be found. And that's what we're going to talk about in this chapter. So where are the electrons? So a ground state electron configuration means one that hasn't been excited. It hasn't had any electricity added into it. And an electron configuration shows how, it's almost like an address. It's the arrangement of the electrons in the orbitals around the nucleus in an atom. It's how they're lined up around the nucleus. It's more than just your circles, okay? It's related to the circles, but it's more than just that. And the way they go in is they go into what's called the ground state. They start by going to the lowest energy possible they can because it's the most stable arrangement for things. And there are 3 rules that define how the electrons are set up in the orbitals. First one's called the Aufbau principle. It says that the electrons go into the lowest energy orbitals first. Those would be the ones that are closest to the nucleus. And when they fill up, then they move to the next one. So it's kind of like a hotel, a very strange hotel. But when you go to this hotel and you say, I need a room, they say, oh, well, you have to live on the first floor. And when those rooms are full, then we're going to put the next people who want to come in on the second floor and the third floor and the fourth floor. And so it's kind of that idea that they want to go into the lowest energy orbital first. And then inside any energy level, so energy levels are those circles, okay? And you're used to those. You've seen those before. So this is referred to as the first energy level. And every energy level has an s orbital. Okay, an s orbital shaped like a sphere. So it kind of looks like the shape of that ring that you're used to seeing. And it's always the lowest energy orbital in any energy level, no matter how far away you are. It is the lowest one, and every energy level has one. So in my hotel, every floor of my hotel has an S room. So on the first floor, it's called the 1S room. On the second floor, it's called the 2S room. On the third floor, it's called the 3S room. And those are the rooms that fill up first, okay, in those floors. And then, unfortunately, what happens is it stops making sense. And the orbitals overlap each other. And what happens is you get this rule to try and help you figure out the order they go in, because they don't go in numerical order, unfortunately, unlike my hotel. So you're going to fill in the order of the arrows. Looks like this. 1S first, then the 2S, then the 2P followed by the 3S, then the 3P, and so far it's numerical order, so that's cool. But then you go to the 4S, because the 4S is actually lower in energy than the 3D. And then after the 3D is the 4P, then the 5S. And again, the 5S is the lowest energy, lower energy than the 4D. And so then the 4D, 5P, 6S, then the 4F. Okay, the 4F is really high up there in energy. It is higher in energy than even the 6S. Okay, they start to overlap a little bit. And then this is the last one you really have to worry about. So this is the idea. So here's your orbitals. And if you thought of them as little rooms, so here's the first room on the first floor, and it holds 2 electrons. This one holds 2 electrons. As a group, each little box here holds 2, but as a group they hold 6. And then you get to the 3S, that holds 2. And again, these guys, each one of them holds 2, so as a group they hold 6. But then that 4S, if you notice, is just a little bit lower in energy than the 3D. And so that one fills up before you get to the 3D, which again, every room holds 2, it holds 10. And then after the 3D, the next in energy is the 4P. And again, 2 rooms, 6 total. 2 in a room, 6 total. And then again, that 4D is actually a little higher than the 5S, so that fills up next. Then the 4D, again 10. Then the 5P, and then the 6S, and then that 4F sneaks in here. Look at how high up in energy that one is. And that 4F, each one of those rooms can hold 2 electrons. And so as a group, they hold 14. And again, it continues on like that. So you can kind of see how many electrons every group of rooms or suite of rooms or whatever you want to call it holds, based on the fact that they have different numbers of orbitals within them and they have different energies associated with them. So the way we're going to do electron configuration notation is you're going to write the principal energy number. This would be the periods on the periodic table. Okay, the numbers on the side of the periodic table. Then you have to have an orbital associated with it, S, P, D, or F, and we talked about that in the last video. Okay, and then you're going to have a superscript, and that tells you the number of electrons that live in that orbital. So think back to that last slide. Okay, the S orbitals can only hold 2 electrons because there's only one of them. But when you get to the P's, they can hold up to a maximum of 6. D's can hold up to a maximum of 10. F's can hold to a maximum of 14 if you need them to. But they go in order. And so this is the way one is written. This is what it is for sodium. Sodium has 11 electrons, and its electron configuration is 1s2. It's not 1s squared, 1s2, 2s2, 2p6, 3s1. I only put 1 in here because I needed this to add up 2 plus 2 plus 6 plus 1. I needed it to add to 11. So I didn't need to fill that all the way up. So that's kind of the idea. You just fill them up in order using the diagonal rule and how many electrons they have. So if I did fluorine, fluorine is 9 electrons. It's 1s2, and then it's filled. Then 2s2, and it's filled. But I only need to get up to 9, and so the next one is 2p, and I could put 6 in there. But I really only need 5 more, so I'm just going to call it that. And you're done. Okay? Magnesium has 12 electrons. 1s2, 2s2, 2p6. So now I'm up to 10. After the 2p is the 3s, and that holds up to 2, and I need it to hold all 2 because I need to get to 12. Okay, iron has 26, and so this gets a little bit longer. 1s2, 2s2, 2p6, 3s2, 3p, p holds 6, so now I'm up to 18, so I'm getting close. But remember, after 3p, it's not numerical anymore. I'm at the 4s, and that only holds 2. So I'm up to 20. And after the 4s is the 3d. Remember, that can go up to 10. But right now I've got 20. All I need to get to is 26, so I'm putting a 6 more in there. Okay? So that's kind of the idea. Iodine, it starts to get pretty long though. Iodine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I'm up to 30, so I'm getting close. 4p6, 5s2. Alright, so that's what? 36, 38, getting there. After the 5s, I go into the 4d, 10. So that's 38, 48. I need 5 more, 5p5. So you basically just have to make sure it adds up, and you have to follow the diagonal rule order. So uranium is 92, and it's a long one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So right now I'm up to 54, 6s2, and then after the 6s, that's where that 4f pops in. 4f14, 5d10, 6p6. At that point, I think I'm up to 86. And then after that, after the 6p6 is 7s2, and then 5f. That's 86, that's 88. I need 4 more, 5f4. Okay, so it can get really long and tedious, but it will always work. Okay, and it's not that hard as long as you remember how many go into each letter and make sure it adds up to the proper number. Okay, noble gas notation is a shortcut. And it works well because what we do is we take the noble gases, because the noble gases have completely filled energy levels. They have 8 electrons in their outermost s and p orbitals, and they are very stable for that reason. Okay, they are quite happy the way they are. They don't want anybody to give them more electrons. They don't want to take any electrons away. They're very happy the way they are, very low energy. And we're going to take advantage of that fact, and we're going to put the noble gas inside brackets. And we're going to replace some of the electrons in the electron configuration by writing that noble gas. Now remember, this is column 18 only that you can do this with. Okay, so either noble gas notation or standard electron configuration to write the electron configurations for these guys. And I already did these guys in on the previous slide. So fluorine, what you want to do, and I'll explain this more in class, is you want to find the noble gas that is less than your element. So in this case, 9 electrons, and you write it in brackets. So helium, and you put a little 2 there. So okay, so it only accounts for 2, so it's not a huge big deal. But then count over. So helium is number 2. The next number would be number 3. And look on the periodic table. And if you look on the periodic table, there are numbers on the side. And if you look, number 3 is lithium. And it's right next to row 2. That means it starts as row 2. And this first group are all S elements. So it's 2S. And it holds 2. And at that point, you can just pick up straight away from the diagonal rule. So helium, 2S2, and then after 2S on the diagonal rule is 2P, and you need 5. So it ends the same way as the last one. Now I realize that's not much of a savings, but let's do iron. So you want to find the noble gas this time that's less than 26. That would be argon, which is number 18. And then if you look at number 18, the very next number would be number 19, and that would be potassium, and it's written next to row 4. And again, these are the s orbital filling. So write 4s, and then just pick it up from there on the diagonal rule. Well, 4s holds 2. After the 4s is the 3d. And I've got 18 plus 2 is 20. Put 6. Done. Iodine. Noble gas less than 53 this time. That would be krypton. 36. Number 37 is rubidium. And that's right next to row 5. So row 5. And again, it's the s orbital. So you might notice a trend. It always follows with an s, and that is true. 5s holds 2. And again, we have to add it up to 53. And we're going to pick it up on the diagonal rule at the 5s. After 5s is 4d. That holds 10. Then 5p. I got 36, 38, 48. I need 5 more to get to 53. So again, it ends the same way every time, whether you do it as a noble gas or you do it the long way. Doesn't matter. Okay, let's do uranium because that was a pain in the neck. So 92, that means I need the noble gas less than 92. That will be radon, number 96, or 86. 86 is followed by 87, and that would be FR, and that's in row 7. So 7S, 2, and then go to your diagonal rule. Look at 7S. What follows 7S? Well, that would be 5F, and then 4. Makes it add up to 92. So either method works. This way is a lot shorter, but you kind of have to get a hang of it, of how to do it, and I'll show you guys in class when I do it in class. Now when it comes to ions, okay, and this is the whole point of doing electron configuration, to set you guys up so you can see why elements get certain charges. At the beginning of the year when we were doing calcium, I said, oh, it's always positive 2, and fluorine is always negative 1, and da-da-da-da, etc., etc., etc. Well, this is the reason why. It's because of the electrons. It's how the electrons are set up around the atom in their address. And so ions are atoms with a charge due to a loss or gain of electrons. We've had this before. Okay, a gain of electrons means it's a negative ion. You're adding, it's got extra electrons added to it. If it loses electrons, it's going to be a positive ion because it's taking away the electrons. It's got more protons this time. And then if you have 2 or more atoms or ions with the same number of electrons, they're referred to as being isoelectronic. Same electrons. That's what that means. Okay, so writing the electron configurations, here's where the shortcut rule is a good idea. If you had S2 minus, well, S normally has 16 electrons. That negative 2 means it's actually up to 18. And if you're doing the shortcut with the noble gases, guess what? Argon has 18. So it is isoelectronic to argon. Okay? Fe2 plus normally has 26, but with that 2 plus means it's down to 24. So it's isoelectronic to chromium, which is argon, 18, 4s2, 3d4. Okay? Barium ion. Now, I didn't tell you what the charge is, so you better look back at your periodic table and go, all right, barium is positive 2. Normally, it would have 56 electrons, but now it's got 54, and so it's isoelectronic to xenon. And you can just write that. You don't have to do anything else. Iodide ion. Iodine normally has 53, but it gets a negative 1 charge, which means it's up to 54, and it is also isoelectronic to xenon. Okay? And so this is the nice thing about the shortcut method. Sometimes you can just write one thing. Okay? It makes it a lot easier. So let's go ahead and see if you guys can practice these. Okay? Oops, let's go back there. And I'll write them on the board, or I'll put them on the PowerPoint in a minute. All right, so doing neon, our aluminum the short way is neon, 10, 3s2, 3p1. Silver 1 plus is 46 electrons, so it's isoelectronic to, I think, palladium or something. Anyhow, that's krypton, 36, 5s2, 4d, 8. As3 minus. As is normally 33 electrons. Negative 3 means it's got 36, so it is just krypton. It's isoelectronic to krypton. And tungsten has 74, so we're looking at xenon. 54, 6s2, 4f14, 5d. What is that? That's 70, so I need to get 4 more. Okay, so check your answers. Make sure you understand how to do this. Long way or short way, you will end up with the same numbers. Now, not if it's this, not if it's an ion that matches a noble gas, but generally speaking, you'll end up with the same ending. Okay, there's a couple of exceptions to the rule, and unfortunately, this is not something we do to make your life miserable. There are actually a lot of elements that don't follow the diagonal rule. Technically, the diagonal rule stops working at calcium. I mean, it really does, and everything just kind of goes to pieces after that, but we're just going to pretend that it doesn't. And we're going to just focus on copper and chromium as our 2 exceptions to the diagonal rule, because those are the ones that are required for the AP exam. And the logic that I've always heard is that the reason why they are different is because half-filled sublevels and half-filled and filled sublevels are more stable than ones that are partially filled. I don't know, it's kind of a weird thing. And so we're not quite sure how it is. So copper, which you would normally write as argon 18, 4s2, 3d, 9, and chromium, which would be argon 18, 4s2, 3d, 4. There has been experimental evidence, not to make your life miserable, that what happens is one of these electrons moves up, makes it 3d10 and 4s1. Same thing happens here. One of those electrons pops up, makes it 3d5 and 4s1, so that these are half-filled or completely filled. And supposedly it is more stable. That at least was the logic that I heard when I was in college. And so my guess would be you should probably just memorize these as exceptions. If you want to put little stars next to them on your periodic table, hope you know or will remember what that means. Okay? So I'm going to stop there and we'll talk about orbital notation next.